Okay, good morning everyone, and welcome to the second part of 4D n equal to 1 supersymmetric field theory course. And glad to see you again and welcome the survivors. Okay, so from last time, let me recap. We did the Sybok duality. This is the duality between two theories, the supersymmetric QCD, which I use the shorthand notation because I'm too lazy to write the whole sentence, right? So contain NF flavors of chiral, and in the anti-fundamental of SUNC, and Q tilde in the fundamental of good point. And the NF chiral of fundamental chiral multiplet in the fundamental with zero superpotential. And the magnetic theory, you reverse the arrow. And this is again the quark, anti-quark, but you have Sybok singlet. You remember this? In type, you can view it as NF times NF matrix with this superpotential. And NF NC prime, the new gauge group, is NF minus NC. Okay, so this is from last time. Gauge symmetry does not have to match, do not have to match between two sides because there are redundancies of the theory. Global symmetry, on the other hand, have to match. Okay, what did we match last time? Global symmetry of the theory. We match gauge invariant operator, meson map to singlet, and baryon map to baryon, anti-baryon map to anti-baryon. Okay, and we provide a very highly non-trivial test called 't Hooft anomaly matching conditions, which mean that fermion in different representation match, right? We compute this, we match 6 number, right? 3 pair, okay, and they match miraculously. So this is achievement, first achievement. Now let me mention something that I have a great pity of, because we have 4 hours left, and we have 2 topics, two very huge topics left. One is supersymmetry index on S3 times S1, and the other is the A maximization. I'm afraid life is too short to do both. So anyhow, you have my notes, so you can read it. But let me point out this supersymmetry index is highly, highly non-trivial. If you look at equation 3.34 and 3.35 of my note, if you have cellular phone, iPad, computer, you can have a look. You see two very complicated expressions. 394 is for electric theory. This is called supersymmetry index. It's a generalization with an index, if you like, for electric theory. 395 is for magnetic theory. And if you wonder what are these guys, the gamma is defined in 9.21. So it's an infinite product. This is called elliptic gamma function. And the supersymmetry index can be written in terms of elliptic gamma function. Okay? This I cannot explain to you, I'm sorry, because time is limited. But if you look these horrible expressions, they miraculously match in 9.36. And this is highly non-trivial. This is a result proved independently by mathematician, actually. This is Eric Rains. You can see theorem 41 in reference 31. This paper came out in 2003, around the same time as the matching of this. And it's matched perfectly. So this is another miracle of a Sybok duality, okay? That it passed all the non-trivial tests, including this one. Unfortunately, I have no time to explain to you each term in the expression, but just to give you an idea that this is highly non-trivial matching on top of the 't Hooft anomaly matching conditions, okay? Now, let me move on to the case where I promised to do, but I didn't have time to do last time. You remember that we assumed that Sybok duality of this form, NC should be greater than 2, greater than or equal to 2, and NC prime should be greater than or equal to 2. And I promised that if it's below 2, you have to modify a little bit. Now, let me mention. Okay? So of course, let's consider the case where NF equal to NC plus 1. Okay? So the dual theory has SU1 gauge symmetry. What do you mean by SU1? Of course, it means trivial gauge group. This is dual to a Wess-Zumino model. Okay? And if I rewrite everything, because now you have operator map between the two theory, right? So operator map works like this, that you call meson in this theory, a singlet in this theory. So you can rewrite everything in terms of meson. The baryon map to the baryon, so I can just rename it and call baryon. I put star just to make everything less complicated. Otherwise, you have a lot of indices, okay? So this is the result. So you might ask me, okay, how can I derive this result? There are honest way to do it, and there's a way to cheat it. So an honest way to do it is in the note. So I have no time again to go over the detail, but the idea is as follows. The idea is you start from Sybok duality of this type. Okay? You give mass to certain flavor on this. Of course, giving mass to this thing will make some meson become massive. Okay? You can map it to give mass to this thing. Then you integrate both sides out. Then you write down the new duality. So in this case, this is exactly what I did in the note. Okay? So please read it, and if you have any question, do let me know. But I will state this result, and I will use a second method to show this to you. The second method is basically to tabulate the charge at any charge that can, any term that has R charge 2 entered in the superpotential, okay? And you match everything using the mass dimension and all the charges. So let me do this thing. So suppose I claim that this is the effective potential. How do you know that this is consistent with all or what we have? We tabulate quantum numbers, right? So of course, they're all neutral. Both sides has to be neutral under SUNF, which is NC plus 1, right? Symmetry. Now, let's look at these things in more detail. So let me tabulate it here. So all of you can see the effective superpotential, right? So let me look at the term in the bracket. I denote it by dot, dot, dot. This is lambda to the B0 in the front. B0, to remind you, this is one loop beta function. You remember what it is? 3NC minus NF. Okay, so it's 3NC and our NF is NC plus 1. That's why I write a factor in the front like that, okay? And then you have W effective. Then you have mass dimension. Then you have U1A. And then you have U1R. This is already quite strong enough to fix the terms in there, up to coefficient. Of course, this method doesn't let you fix the coefficient. In order to fix coefficient, you have to use method of integrating our mass, okay? But, okay, so mass dimension, who can tell me what mass dimension in the bracket is? Please. So meson has two quarks, okay? Each of them has charge 1, okay? Mass dimension 1. 4 minus 2 over 2, okay, in 4 dimension. So now you have determinant. You can work it out from either term, okay? Maybe determinant is easier. It's NC plus 1, right? So it's 2 times NC plus 1. Okay? So now the lambda here, lambda has mass dimension 1. So this is 2 times NC minus 1. And since you have to divide this dividing by this, so you have 3. And remember, what's a superpotential? What's the mass dimension of superpotential? 3. I emphasized in the first lecture. This is going to be important. Here it is. So you match anything that compatible with all of these tables can enter. This is the quantum rule, okay? Up to undetermined coefficient. This I cannot help you. Now look at U1A, for example. Who can tell me what's the U1A here? Remember, quark and antiquark has the same U1A symmetry, which is 1. Okay? So again, determinant has this number. Who can tell me what's this? Lambda to the B0. We tabulated, you remember? It's 2NF. I know this charge under U1A. This 2NF. NF is NC plus 1. So indeed, superpotential has charge 0 under this. This is nice. It should not charge under U1A. Superpotential can only carry charge 2 under R symmetry. Now the last one is stringent one. So what is U1R? You remember the R charge, the non-anomalous R charge that we use? It's, for quark, is this guy, right? 1 over NC over NF, right? Which is now is NC plus 1. You agree with this number? This is for one quark. Meson contains 2 quarks, so it's 2 times. And then you have determinant of the size of the NC plus 1 times NC plus 1. So this is this one. Okay? You simplify, you get 2. You agree? This, since our choice of R charge is non-anomalous, this cannot carry charge under it. So this is 2. So this shows that this enter in a correct way. You see, this is highly non-trivial for these 2, whereas it's trivial in these 2. It's highly non-trivial here. So with this charge, we can write an expression which is compatible with all the charge and the mass up to coefficient. Relative coefficient, this I cannot determine using this method. But honest method of integrating out can lead to this expression. Okay? Now, actually, this method is powerful. I mean, you can fix a lot of things using simply tabulate the charge in this way. Okay? You know that lambda has to be there because one loop beta function is not 0. Lambda has to enter by transmutation. Okay? That's why it's participate. And then you look at the combination of gauge invariants such that, first of all, it has to be neutral under SUNF times SUNF. Then you tabulate all of these things. You can kind of guess this type of expression. Okay? Now, for NF equal to NC, again, the trick is you start from this model with this superpotential. You give mass to one flavor, right? So from NF equal to NC plus 1, you give mass to that flavor, integrating out, and then flows. What you will see is that you will obtain this relation. Again, this the detail is in the note. I don't have time to integrating out in front of you, but it's integrating out. Okay? So you have this again. What we can do is that you can also guess this type of relation already. Actually, there are even more hints to this relation. You remember that we derived in classical moduli space, we discussed that this is just determinant minus star b tilde equal to 0. This you remember from the classical. This we did from when we first do SQCD, right? Now you see quantum effect. Put lambda to the 2NC. Of course, in classical, we wouldn't have lambda. Lambda is purely quantum effect. This is dimensional transmutation. And now you see that from classical, I emphasize to you that there is a singularity where M, B, and B tilde are 0, right? Look like a cone in this picture. The cartoon look like that. This is a singular point. Right? Here, singular point was removed. So the cartoon look like this. And this is about scale lambda. Roughly, this is how you should have intuition. Of course, it's complex and so on. I don't know how to draw this, but this is the picture. So the singularity here got resolved by quantum effect. Okay? And now, again, you can tabulate the consistency. So you can look at the left-hand side and you can look at the lambda B0. And now B0 will become 3NC minus NC, which is 2NC. This 2NC on the right-hand side is generated by the lambda to the B0. It's always like this. This is how transmutation works, basically. It comes with lambda to the B0 always, okay? Okay, so now let's look at the mass dimension, U1A and U1R again. Okay, so the left-hand side, okay, the mass dimension work like this, right? Instead of 2NC plus 1, now you have 2NC. And indeed, it's mapped with 2nc because lambda has mass dimension 1. Okay? U1a, each quark has U1a1. So determinant has two quarks. So M has 2 quarks and determinant has 2nc. Right? And the lambda to the B0 has anomalous charge 2nf. But nf equal to nc. So it's 2nc. It's match. So now U1r, the R symmetry, again, you have to use the non-anomalous value that we propose is 1 over nc over nc times nc, right? Which is turn out to be 0, and this is 0. Sorry, this is a bit small, but you can look at the note. Okay, so this is consistent with the charges that we have. Okay, right. So now you see, this is a special case of Sybok duality because if you dualize it, you would say that nf equal to nc. When you dualize, you get SU0. What do you mean SU0? This is the picture that you should have in mind. It's a theory where it's constrained on there's no dual theory. It's just constrained on the moduli space, basically. Okay. If you want to write down this in superpotential, you have to put Lagrange multiplier. Okay, W equal to some Lagrange multiplier times this term. This will be your correct effective superpotential. Okay. Now let me do the last case. This case deserves proper explanation. Cannot skip this part and go fast. This is the achievement of the supersymmetric field theory also. Okay? So when NF is less than NC, again, the trick is to integrate out one flavor. Okay? Trust me, it works. Integrating out one flavor or K flavor or whatever flavor from this theory. So when you integrate it out, the number of flavor falls. Okay? So now you can reach NF less than NC. Once you do that, you get this effective superpotential, okay, by process of integrating out. This is done in 8111 up to 8115 in my note, okay? So you see I give mass to the flavor. Indeed, I didn't lie. 8111 is giving mass. And then you differentiate with respect to the meson, and then you obtain the relation, then you integrate it out, okay? So you obtain this relation. Again, let me tabulate two things. There is some problem here with the R charge. This theory doesn't have a non-anomalous R charge, unfortunately. The reason is that if you use the value that we have, okay, let me point out why. This theory is quite weird, but let me tabulate this thing. So you have, okay, lambda to the B0. Lambda to the B0, this is 3nc minus nf. This always the same. Let me tabulate determinant of M, and let me tabulate W effective, okay? There are two things that I would like to use, mass dimension and U1A. Okay. So let's look at this table. Let's look at this thing for now. I explain to you why this thing is enough to fix it. So this is mass dimension. Of course, this is 3nc minus nf. You agree, right? Because lambda is mass dimension 1. Determinant of M is 2nf. Because M carry 2 quarks. M is an nf by nf matrix. So this is 2nf. And indeed, if you do this, you divide it by this, you get 3nc minus 3nf. In order to obtain the right superpotential, you have to normalize it, put this to the power, right? 1 over nc minus nf. So this has precisely dimension 3. So only mass dimension already fixed you to this form. Now to be sure, you can use U1A also. U1A, this carries 2nf. This we show, okay? Determinant of M, again, is 2nf. And indeed, superpotential has A charge 0, which is perfect. So it fixes us in this form. Some of you will say, I don't like this at all. You have M down. What is going on here? Yes, so now let me explain this part, okay? First of all, you see that we start from, this is, if you remember the Lagrangian that we wrote down something like this. Okay, NF can be less than NC. We analyze. You remember we analyzed this case classically, and we say that there is meson matrix, right? The parameterized NF square dimension moduli space, right? We derive that. And look at this. I declare my superpotential in the Lagrangian to be 0. And what I get at that when I do renormalization group flow, I get a non-trivial superpotential. Right? I start in my Lagrangian with 0 superpotential. This is what I promised to you. And now by tabulating charge, by integrating out, by doing quantum effect, give me this thing. Okay? Of course, in classical theory, we wouldn't have lambda. Lambda is, again, transmutation. But transmutation forced me to write everything in this form. Up to, well, this method will not fix this form for me, but it will fix this form for me. Okay? So what's going on? So this is quantum correction, for sure. And this is consistent with the charges we have, and so on. And very nice. It's come in this form. Okay. So, and first of all, you can ask, okay, this is quantum effect. Can we derive it perturbatively? And if you remember what I said, the dimension transmutation come with the instanton effect, right? 1 over g squared. So this is the instanton effect, is non-perturbative. So this is non-perturbative correction to superpotential. You remember I prove, well, I give you argument, superpotential never get renormalized to all order in perturbation theory. But I warn you that it can get renormalized non-perturbatively. And this is a prime example of non-perturbative correction to superpotential. Okay? This has a name. This superpotential is called the Affleck-Dine-Sybok superpotential. It's a notable non-perturbative correction to superpotential, basically. This is one of the most important, okay? So indeed, the way you can derive it, there are two ways. I give you two ways. One is tabulating the charge. It will fix this up to constant in the front. Second way is to integrating our mass. This will fix the constant in the front for you, okay? And this is the correct one. Okay, so now there is a effect which very important once you write down this superpotential. One effect is lifting of the vacua. So if you write it schematically like this, W effective NC minus NF, NF less than NC. So it goes like this. Think of determinant as this guy, okay? You agree with me? You can roughly think of it like this. Now your effective variable, you don't have quark anymore. In the low energy, you only have meson. So if you look at this, you see that the scalar potential derived from this is the MW mod square. You remember this? Scalar potential is the derivative of superpotential mod square. You get approximately m to the minus 2nc over nc minus nf. Observe that V never be 0 for all waves of m, for all vacuum expectation values of m. Right? This is clear. So what happened? You don't have supersymmetric vacua anymore. So we showed earlier that there's a bunch of classical vacua parameterized by meson matrix. You remember that what we did in when we first did SQCD? Now there's no vacua. So no SUSY vacua. So, and where does this come from? This comes from precisely this superpotential. Without this superpotential, you would conclude that there is supersymmetric vacua because W equals to 0. This is a classical picture. Okay, so let me emphasize this is classical. Okay, and this is quantum picture. So, no SUSY vacuum. So this means that the quantum effect lifts the vacuum that we showed in the first lecture. And in this case, the vacua are said to be runaway. This is the technical term of this type. So when you when you hear people talk about runaway vacua, this is this type of thing that you should think of. That non-perturbative correction generates something like this, and the vacuum is wiped out. The classical vacuum is wiped out. So this theory doesn't have a supersymmetric ground state. So there's no point to talk about non-anomalous or R charge or this kind of thing, because quantum F, there's no supersymmetry to talk about in the first place. Okay? Good. So now let me, there's no vacuum, no supersymmetric vacuum. There's it's non-zero superpotential. Non-supersymmetric. There is vacuum. Well, in non-supersymmetric vacuum, you allow minimum of the potential. There's minimum of the potential. Depend on the M. I mean, so the M. You can start from whatever, well, okay, in this case, it go away, right? So, well, you can use the point where, up to you, it's a mod of M, so it's far away. Then you might have a very far away in the value of M, which approach, but not really the local minimum anymore of V, okay? So in this sense, you can also say that if you trust this, if you only have this W effective, this is the result, and this is at infinity, you would go to 0.
But then how do you compute the vacuum expressions of value if there's no vacuum? In order to calculate VEFs, I need a vacuum.
Yeah, but there's, well, you can declare to be the value of any web there's non-zero, right? So I claim that there's no vacuum in this theory, basically. Am I saying something wrong? There's no vacuum.
No, maybe something quite clear,
Is it better for you? Yeah, that's the point. This quantum effect breaks supersymmetry.
Is there a way to break supersymmetry but still have a non-trivial theory? Because I mean, it's a problem not to break supersymmetry if we believe that supersymmetry exists. This is a general fact of all problems.
No, breaking SUSY this is a literature by itself, okay? So there's a huge literature on how to break supersymmetry dynamically. This is one way. There is also a lot of ways, such as you can break it using Kähler potential. This I use it with the superpotential. There's a way to do it with Kähler potential, and so on. I mean, I will not touch that subject. I mean, it's a rich subject by itself. But you can break it in many ways, spontaneously break it in many ways, okay? This is one way. So the vacuum just run away. So at infinity, you might have a 0, but no. In this case, for finite value of M, you never have it, okay? Now, suppose that you decouple all flavor. Oh, I'm go over my time limit now. So let me wrap up. So if we decouple all flavors, what would you imagine? You would obtain n equal to 1 pure super Young Mills. So we have W effective equal to NC lambda to the NC 1 over NC. And now you see why the power 1 over NC is significant. It's give you precisely NC vacua, right? This is gauge-Gino condensation that you saw. Okay? Since the UV Lagrangian of the supersymmetric Young-Mills theory is d2 theta TUV over tau UV over 4 pi I trace WW. We obtain, you remember superpotential enter d2 theta, right? So you can match this and this. So we obtain trace of WW proportional to NC lambda to the 3NC 1 over NC. So this is reproduced NC vacuum of super Young-Mills. Okay, so this ends my presentation on the SQCD. Now, is there any question? Yes, please.
The general orientations of electromagnetic duality, is it somehow embedded inside the duality, or is it?
I would say that in the case that we can show using the confinement and between electric magnetic, it's clearer if you use SO gauge group, I think. Then you can kind of see the electric magnetic duality. Yeah. You can see that in SO case, you can see the exchange between magnetic and electric certain spectrum. In SU, I'm not so it's not so clear, to my knowledge. Okay. You can look at the SO case in the paper of Interligator and Sybok. Okay, they work together. They have a very clear explanation in that case. The paper has the title of oblique confinement. Oblique confinement. Yes. So, any other questions? If not, let me use the rest of my 3.5 lectures to do even more modern topics. It's not so modern, 2000, of a very important one called DA maximization. Okay, this is also a great tool in supersymmetric field theory. Our focus will be on superconformal field theory now. I will tell you the significant why this is a rich subject, a super rich subject. Okay, so DA maximization. Okay, so let me first mention certain important point, which is some of you have seen some kind of idea, but not pinned down. Okay, so there are some important points. Some of you might know this already, but if you don't know this, you can go through it with me. Number one, supersymmetry relates the stress tensor T mu nu to the U1R current so they are both in the super multiplet Okay, so let me write this super multiplet down once and then you will see it, okay? So again, I have to use superfield. I don't know how to do curly T, I will do it like that. Alpha alpha dot x theta theta bar. These are space-time, these are supersymmetric coordinate. Then you have JR alpha alpha x plus theta beta S alpha beta beta dot x plus theta bar beta dot S bar alpha alpha dot beta x plus, let me continue here, theta beta theta beta bar T alpha alpha dot beta beta dot x. Okay. Okay, so let me explain each term. So this multiplet is very special, so let me explain to you. The first component in this multiplet contains J of R, okay? J of R is the U1R current. If you see alpha alpha dot and you don't like it, you can convert it to the mu always with a sigma matrix, okay? This is the R current. S and S bar, this is called the supercurrents. This is in supersymmetric theory. And there is a stress tensor. Again, you might be familiar with this. If you don't like alpha alpha dot, feel free to change it using a sigma matrix, okay? This is stress tensor. Okay, so you see that they're really in the same multiplet. So if they have to transform together. Okay? This is crucial. This is point number one. Ah. Hmm? The S has, there's no balance. Yeah. I'm sorry, it's just a typo. Better? With the okay.
But I mean, you can convert them to space-time indexes.
What happened?
So how do you pass from the S with spinor indices to like?
I contract with sigma. Is it okay? No.
But sigma has two spinor indices.
Sigma.
You have three there, so you have one spinor index. Maybe it's a downward rather than.
Which blackboard you are talking? This one?
Yeah, if you want that with the space-time index.
Oh, you want to write S in space-time index?
Yeah.
There's a, well, you can, no, you cannot, it's the lowest component of S is always spinor, so you always have one. It's like a Gino. When you have W, you have to, the superfield itself, the lowest component is fermion. This lowest component has a SUSY generator. That's why it's, now I understand your question, thank you. Yes, the lowest component is fermion. You can have superfield which lowest component is fermion, right? Like in Gagino superfield. Okay? Now, we call the charge associated with this U1R current RT. Okay? Let's call it R with the subscript T. Now, you understand why I put subscript T. T stands for trial for the moment. Okay? Number two. Away from the fixed point, the conformal fixed point. RT is not really conserved. So if you talk about renormalization group flow, in the middle of the flow, for example, RT is not a conserved current. Why? This is because it's non-conservation. Is related to, by supersymmetry, to non-zero T mu equal to 0. You agree? Away from superconformal point, this is non-zero. And by SUSY, is related to R of T. This breaks scale invariance. This is basically is non-conservation, is related by SUSY to this thing. And this is the lack of the scale invariant. Okay? So away from superconformal point, this is not a conserved current. Okay? Because supersymmetry related this J to the T. And T mu is non-zero away from superconformal point. Therefore, it's non-conserved. However, as the theory flows to an SCFT, a superconformal fixed point, RT can approach a value R star. Okay? And now R star has to conserve. Okay? So, any 4D SCFT necessarily have a conserved current U1R star symmetry with the U1R star being a subgroup of the 4D superconformal group SU2,2/1. So this is a significance of this R star. Okay? So you start from RT, then only it's not really conserved. But if you hit the fixed point, then you have to have a conserved current, a conserved U1R star. This U1R star has a name. So I go a bit slower here because these points are highly important. This is really the gist of the why we have to start the whole program of this, okay? So we refer to U1R star as the superconformal R symmetry. Okay. Okay. Point number 3. So now you know when people talk about, this is superconformal R symmetry, you know it's very special, okay? There is some special point there you have to discuss. Okay.
Can I make a question? All right. Usually, I mean, from here we
Yeah.
And usually we have anomaly matching, I mean, on a flow. So what I understand from this is that VR charge, VR current in that multiplet continuously changes
That's right.
on the flow. I mean,
That's right.
It's
It's not a conserved current. That's why.
no, and it's not always the same current that enters in.
That's the point. Yeah. The point is that there can be many choices in general, okay, in non-supersymmetric theory, and this is not unique at all. But when you have a superconformal point, is the current, the U1R star, okay? Yeah, there can be many, yes. Usually, and in SQCD, for example, you fix using anomaly, okay? This is a simple theory. In general, there can be many. And along the flow, I mean, this is not necessarily conserved, yeah. So RT, there can be many choices, indeed, as you said. The supersymmetry relation R mu related to T mu nu implies many results. Some of you have seen this, but let me go over. These are important since this is my last part, and this is so crucial. Let me emphasize all of them again. Number 1, 3.1. 1. Delta of O, we have seen, has to be greater than 3/2 of R star of O. For all gauge invariant, spin 0, operator O. Okay? Delta is the exact dimension, operator dimension. And R star of O is the U1 R star charge of O. You have seen this, right? Unfortunately, I didn't have time to derive it, but you have seen this thing. And I emphasize that you have to apply this to gauge invariant only, because otherwise the Hilbert space is not BRST invariant, right? Well, yeah, if it's not gauge invariant, you can do quantum transform, you can do a gauge transformation, and in vacuum is not unique. But that's why this is true for all gauge invariant, okay? Now, you can also say, point number 2, let me erase this. Point number 2 is for a chiral primary operator. So I emphasize it has to be chiral, okay? Primary operator. Delta of O is equal to 3/2 R star of O. This you have seen, okay? And the additivity of the U1R charge for composite operator implies that they form a closed OPE ring. Okay, let me explain this point a little bit more later with additive operator dimension. Okay, so because of this, you can see that you can multiply all the composite operator together, and there's still the chiral. Well, when you multiply chiral operator together, there's still chiral. First of all, I derived this in one way is that there's no short distance singularity. You remember, if it's chiral, this is when I do K-Gino condensation. So they form this is called chiral ring. Okay? And when you multiply them, what you can do, you add R charge together. But because of this relation, if you add R charge together, you also add their dimension together. Okay? So basically, this is, at the superconformal, this is a very nice result. Okay?
So, can I ask you, is there any link with the fact that the operator is BPS?
Yeah, it's a chiral primary operator, meaning that it's annihilated by the, so primary, yes, this is coming from. I don't talk about descendant. Descendant means you hit it by derivative. This is the descendant, okay, in the superconformal, in the conformal field theory language. Yeah. So, and the third one, this is what we go over in detail. We went over this in detail. Number 4. Okay, number 3, unitarity bound. You might say, why I keep revising all of this? I will use all of this for sure. Is that delta greater than 1 for spin 0 operator. Okay? Implies that R star of O has to be greater than 2/3 for spin 0 chiral primary. Operator. Okay? With R star of O equal to 2/3 if and only if O is a decoupled free field. Okay? And point number 4, R star is anomaly free. Precisely if the NSVC beta function vanishes. This we have seen as appropriate for the CFT. Okay, so indeed beta function should vanish at this point. So this is the important point. You have seen this, so I will not, this just to remind you basically, but these are highly important. If you don't learn much from this, please learn these points. These are highly important. It will apply to any superconformal theory. Okay, so this is a set of important facts. Now let me move on to some new thing that I haven't mentioned. The next topic is the conformal anomalies. Okay. What is conformal anomalies? It says that the trace of the stress tensor of a 4D theory in curved space is non-zero. If you put it on curved space, T mu mu is non-zero. Okay. So it says that the trace of the stress tensor in 4D CFT is non-zero in curved spaces. So you probably have seen this relation somewhere. Who have seen this relation before? Could you please raise your hand? Okay, not all of you. Okay, so let me explain. So when you put conformal, conformal, this is conformal, not necessarily super conformal at the moment on the curve space. Okay, you compute the T mu mu. It's general, it's non-zero. It depends on two type of coefficient, A and C. This is Euler density, and this is Weil tensor square. Okay, so E4 is called the Euler density. This E4 equal to, oh, this is a mess to write down. 1 mu 2 epsilon rho 1 sigma 1 rho 2 sigma 2 with the R mu 1 rho 1 sigma 1 R mu 2 rho 2 sigma 2, and this is Weil tensor of your curve space, whatever you put on. Okay, so there are two coefficients, this is A and C. This will play some role in our discussion. Okay, so this is about conformal field theory on the curve space time. Okay. Now, what's the significance of these coefficients? A will play important role for us, and A has a very long story actually. Well, the coefficient A can be considered as the integral of the energy momentum tensor on the force sphere. Lovely, like this. So since you integrate this point on the force sphere and you get A, basically this can be thought of, this is expected to provide an effective measure for the number of degree of freedom of the theory, such that as we integrate out high momentum modes, A decreases along the RG flow. So think of the Wilsonian renormalization, right? When you flows, you integrate out the high momentum mode, and the degree of freedom should decrease, right? So this is, so in other words, if you compute this A in the UV, it should be greater than A in the IR. Okay? The first person who conjectured this is Cardy. And this comes in the name of the A theorem. This was amazing. It was proven in 2011 by another lecturer with his collaborator, Zohar Komakotsky-Schwimmer. This is reference 37. I highly recommend you to read this paper. It's a beautiful paper. It's very simple to read. It has a lot of physics in it. The proof is really nice. Okay, I don't have time to do this, but just to refer to you, this is called A theorem. This is true in any 4D quantum field theory. It doesn't have to be supersymmetry. Okay. Right. Now, yes. S4 because I want to extract A. Yeah, roughly. This is just to motivate you that it's related to degree of freedom. Yeah. So the conformal anomaly in general, in 2D you also have this kind of quantity, which unfortunately is called C, but it's A, in the sense that it's in the front of the Euler. You have similar theorem. That it's also count degree of freedom. So this is a generalization of the 2D version, if you like. But I write it in this form on S4 just to motivate you that this is related to number of degree of freedom. Okay.
But that's no fundamental reason for S4.
The not on in general I want to pick S4 because I just want to extract this quantity basically.
Because I mean the X index in conformal theory usually is related to the central charge of the conformal theory.
Yes.
And in this case, instead, at the conformal point.
No. I'm not in. Well, okay. Say again. Sorry. At the conformal point.
I mean, the Cardi index is the central charge of the conformal theory.
Okay.
So it's non-zero in general at the conformal point. While this one is the integral of the space, it should be zero at the conformal point.
No, this is not because you put in curved space. This is highly important. You detect this anomaly by only putting in curved space. Okay, this is highly significant. Yeah, and I pick one particular curved space here just to motivate you that why it's related to degree of freedom. Okay. Now, another important result, which is older than the proof. Yes.
So that's in Euclidean space, right?
Yeah.
But is that obvious that it holds also in symmetry?
Usually I do all of these conformal algebra in Euclidean. In Lorentzian, let me see. Well, I'm not sure about this signature issue. I have to check. Probably doesn't. Yeah, this point I have to check, but I'm not sure. Usually when I do conformal field theory, sometimes it doesn't matter, sometimes it matters. It depends on the question that you ask. When I derive algebra, conformal algebra in this paper, I usually do in Euclidean. But okay, it's a good question, yes, whether the signature dependence or not. Whether you know the answer? Yeah, okay. Yeah, this is a sophisticated question, by the way. You ask this to a lot of things, and then you have to recompute usually a lot of things. Yeah. Okay, but then the conformal anomalies. A and C can be related. Let me state this and you can take a break, okay? To the superconformal asymmetry of the anomalies. So okay, so this is the relation, quite an important relation. This is a very powerful actually. So if you look at the left-hand side, this is A and C as we stated in the, erase it? Okay, in the T mu mu, okay? You can relate this T mu mu to the trace of this R. I don't know, you remember this trace of R and trace of R cubed? These are called 't anomaly because you put three of them, trace of R cubed, imagine the triangle, you put R star, R star, R star, and you compute the trace over all fermion. This is trace R cube, trace R star cube, okay? This one, you remember, you put R star in one, you put two gravitational. This is a gravitational anomaly of the R, okay? Then this relate to the A. In C, you can do the same with the different coefficient, okay? So this is an old result back in, I think it's in reference 38. It's Anselmi, Friedman, Guisaru, and Johansson. This is from 97, this first relation, okay? So one way, okay, let's take a break and I will discuss this further. This is extremely powerful result, which you can do a lot of things with it, okay? So yeah, let's take a break for 10 minutes and we come back. Okay, let's resume. So this conformal anomaly can be related to the Toft anomaly by these guys, okay? So there are two terms that you need to consider. One is the trace of R cube. So you look at a triangle diagram with the R star, R star, R star, and trace of R is, as I said, this is gravity, gravity, and R star, okay? This is the trace R star. Okay, so what's the consequence here? The consequence here is that the right-hand side is Toft anomaly. So if we assume that R star symmetry is conserved along the RG flow, so meaning that in the UV you have R star, the same R star which is non-anomalous, okay? You go down, it's also, UV is a free conformal field theory, for example, and you go down, is a strongly coupled conformal field theory, and R star is still conserved along the RG flow, then you can either compute this either in the UV or the IR, because Toft anomalies have to match in the UV, in the IR, right? So this is the statement. In SQCD, for example, you feel free to use your classical Lagrangian to compute this quantity, and you can declare that because of Toft anomaly, this is also the result for the strongly coupled conformal field theory, for example. Okay, is it clear for you? This is a consequence. Mm-hmm.
I don't understand. If we just saw the previous hour that the R symmetry is in general anomalous outside the fixed point.
Yeah, that's the point. I mean, in general, if you pick a general away from the fixed point, the R star current might be different from the RT current. But if I assume that there is such an R star, this is the important one. That if we assume that there's such an R star that connects UV to the infrared, yes, then you can do the Toft anomaly matching by computing this in the UV or computing and declare that your value is the same as computing in the IR. Okay, this is why it's a powerful result, because you can use Toft anomaly matching on the right hand side, provided that there's R star. If you don't have this R star that conserve along the flow, forget about it.
So I think I misunderstood, but did we earlier show that AIR is always smaller than AUV?
That's the point. AIR smaller is true. In non-supersymmetric theory, you're not guaranteed to have R star. That theorem works in general. Here, there's a special R. Think of supersymmetric QCD. There is a special U1R, which comes from zero beta function. It's the same in the UV. It's conserved along the flow. Then you can compute this using in UV, using classical data from the Lagrangian, and declare that this is the same value as superconformal point, the A and C for the superconformal point. Okay, this assumption is there. If you don't have this special R star that conserved along the flow, forget about using Toft anomaly. Toft anomaly you can match only when there is this special R star which conserve along the flow. Okay. Sometimes It's even that this R star become emerging in the IR, and this also useless for this thing because it's not there in UV. Then what's the point? Then you compute two different things. Okay, but if there's such a thing, then you can do. This I will demonstrate in the example. Don't worry. Okay. So let's compute. That's why it's important to write this formula using star, you see. I always writing it like that. I mean, some people neglect it, but this is important. So example, free chiral multiple. Multiplet. Okay. In this case, R of phi equal to 2/3, and R of the supersymmetric partner is 2/3 minus 1, which is minus 1/3. Okay? So A is just 32, 3/32, 3 times minus 1/3 cube minus 1/3. This you agree? You have only one fermion. You have to use fermion to compute the trace. And this is the value. You should get 1/48. And similarly, if you compute C, you get 1/24. This is an important number. Okay? So 148, 124. A free vector multiplet. The gaugino has R charge 1, and this is already a fermion. So you can compute this. 3, 1 cube minus 1. You get 3/16, and if you compute similarly, you will get 1/8. Okay? This is an example of the important guys. Okay? So let me discuss briefly how do you prove this relation. I will not do it in detail. I refer you to reference 38 and 39. There are two ways of doing it. Let me pick one way. This is in original paper. So you have to look at the anomaly of the oh, I erased. It's on the previous backboard to here. There is a curly T. You look at anomaly of this guy. It relates you to the while, and there's a superfield correspond to the while tensor. Once you relate an Euler density, once you relate to that, you relate anomaly in the T. T contain the R current. A and C related to Y and Euler. Okay, so anomaly in that superfield relate the energy momentum tensor, which is the R star, okay, to this A and C. So everything follows from the superspace anomaly of the curly tau, basically. That's roughly how it goes. Yeah. Okay. So, okay, now, also Toft anomaly also tells you another thing. This is another test for Sybok duality. So if you compute A and C using electric theory or using magnetic theory, you should get the same answer. Okay, this is another thing to do. Okay, so let me demonstrate how to compute this in SQCD. So let me leave that board. This you should do as an exercise, okay? It's anomaly, so it should match. So if I look at this formula, I will compute only A, okay? I'll leave 3. Let me normalize 32/3 in the front of A. So you compute 3 times the trace, right? So basically, you have quarks and antiquark, and you take fermionic partner of them, right? So how many of them? There are 2 NC times NF. NCNF come from quark, NCNF from antiquark, so you have 2 of them. Times 3, you have 6 NCNF. Times the R charge of Q minus 1. Q. And remember, you have to use R star. This we did, right? The 0 R star coming from the 0 beta function, right? We did it in detail, so we use that value, which is 1 over NC over NF. Okay? This you can plug in, minus 2 NC NF RQ, again, minus 1 Q. This is the cube term. Oh, did I say something? 3 times. No cube, I'm sorry. This is the first term. Yeah. Okay? Now you have to do, this is the contribution from psi of Q. This is psi of Q tilde. Okay? This is, you agree with me? So this is contribution from Q tilde. Is this all? You have other fermion left called Gaugino. You have to do that also. The Gaugino introduced 3 is in adjoint representation. You agree? And the second one is NC Q minus 1. Right. So if you simplify this, you can write it as 2NF squared minus 3x to the 4 plus x cubed minus 1 over NF squared with x equal to NC over NF. And you can do for the other coefficient also, but let me not do it in detail. This is just to give you example. An exercise is to do this in the magnetic theory and match it. Okay? I guarantee it match. Okay. Now let me mention also another important property of A and C. So, sorry, this is SQCD in the conformal window. Okay. So let me mention one more thing. This is called the Hofmann-Mauthausen bound. This we don't need it, but since we already go this far, it would be wrong not to tell you some more property. Okay. So in supersymmetric and non-supersymmetric theory, there is some bound on the ratio between A and C. This you can test many things, right? So let me state. Again, I will not prove this. This would require a lecture by itself to do this. It's called the Hofmann-Mauthausen bound. I think original paper is in the paper called Conformal Collider. It has such a cool name. So yeah, they look at certain very clever of a correlator, some energy correlator basically, and they managed to obtain some important result which I like very much. It's the ratio of A and C. Okay, you can even do this for non-supersymmetric theory. For n equal to 0, I tabulated nicely in my note, but you can have a look. Okay, so let me quote one thing. In n equal to 0, meaning that you don't have supersymmetry, this bound is this one. And n equal to 1, this bound is 3/2 A over C to 1/2. Okay? There is a version for n equal to 2, n equal to 3, and n equal to 4. A over C has to be 1. Okay? So this tells you if it saturates the lower bound, your theory contains free chiral multiplet or free, yeah, this is the free field basically. In this case, this is free chiral. If it satisfies the upper bound, it means that you have free vector field or free vector multiplet. Okay?
Sorry, but isn't the right bound less than the left one?
The right bound. Oh, I'm sorry. You're right. Thank you. I copy wrong from my note. Okay, thank you. It's embarrassing, okay, but okay. Well, thank you. This means you pay a great attention to the lecture. Really appreciate. Okay. Yes. So you can test actually if you happen to do some wrong calculation, it is go out of this bound. There is something wrong with your computation. This is a nice test. I mean, okay. Okay. Just to mention this in passing. Now let me go into the heart of the problem. You can see actually we compute this, right? You can see the ratio, right? For n equal to 1, A over C. It's 1/2, right? This is free. This is free chiral, and this is free vector. You can see. It's very nice. And they managed to prove it for non-SUSY. This is, to me, this is impressive. Okay. Okay, so now let me move on to the the important problem that we have. So let me state the problem, statement of the problem. So number one, how can one identify precisely which possible R symmetry is the special one which we call R star of the superconformal algebra Okay? This is not in general uniquely fixed like in SQCD. SQCD was so simple because we have one gauge group and simple matter field. In general, if I give you gauge theory, actually later you will see one gauge group or actually a bit of matter field, but you cannot fix this using simply anomaly. In SQCD, we were lucky. We managed to identify R star by some method, right? Either you say it's non-anomalous, either it follows from beta function, and so on. But in general, it's not clear. It's not clear how to do this thing. So in general, this is not uniquely fixed by symmetries, as in SQCD. Okay? Now, the point is that if the theory has a large group F of non-R flavor symmetry, with charges F of I, okay? We can make a general R symmetry, also known as the trial R symmetry, by combining the initial R symmetry, R0, with any linear combination of this form. So R trial equal to R0 plus sum over I, Si, Fi with Si real parameter. So if you have flavor symmetry, you can feel free to take the carton. So you have charges, right? You can mix them in the original R symmetry with Si real, okay? Question. A big question. How can we determine the particular value of Si, okay, which produce the special U1R star that belong to the superconformal group SU2,2/1. So now you see this is it has been a very important long-standing field theory problem actually, because if you have a lot of flavor symmetry, you can mix it with the whatever R symmetry you have. Then you come up with the RT, the trial R charge. But you don't know which one is correct, that become this special one, U1R star. And this problem is, has been long-standing in physics until interligator and vect came. By the way, who know Ninja Brian? Yes. Go to YouTube and search for Ninja Brian. This is Brian Vecht at the moment, actually. So, yes, he do the channel, the comedy channel. I think this is quite amazing.
This is what happens when you understand not to be good enough to string theory, right?
No, he's definitely more than good enough. So, a solution by interligator and Vecht. No, he has a permanent position at Queen Mary before he left to do comedy. So, by the way, I should contribute this lecture. Okay, of course, all the mistake, or the imperfection, or the error, I apologize due to me. But all the good part, if you like this lecture, at least a little bit, I contribute to Brian, okay? I learned Supersymmetry QCD first from Brian in Cambridge. He lectured in a workshop. So in 2007. So yeah. So I would like to give credit to him. Okay. So the superconformal symmetry is the unique choice of the trial symmetry RT given above, which locally maximize A trial as a function of Si, 3 over 2, 32, 3 of trace RT cubed minus trace of RT. Okay, so you see here is RT. Of course, RT will be function of S as there, okay? And if you manage to determine the local maximum of this function, then you can determine the right S, which tell you what mix you have to do between this Fi and the R0. So any RT would do. You just parameterize it, and then you solve this maximization problem. Okay, it's very beautiful. Okay, the value of A trial at this local maximum is then the central charges. So someone asking me whether the central charge, here it is, central charges A of the CFT. Okay. This procedure is called A maximization. Okay, and there is an important here. So you might ask me, okay, is this guaranteed to have the local maximum? The answer is yes. In general, star, okay, because star is a cubic function, there is a unique local maximum, but no global maximum in general. Yeah. So basically, you take this as a cubic and you solve the cubic equation in general. Okay. If you solve this cubic equation, you get a solution. Usually, these are algebraic number. Okay. Then you can well, it's not. Some cases it become rational, but in general, no. It's usually algebraic number. Then you can determine the right R charge and then do this computing the A at a superconformal point. I'm afraid that I might have to omit the proof till later. The proof is also beautiful. It uses a lot of properties of, let me see. Let me do one example first in the last 10-15 minutes, okay? And then in the next lecture, if we still have time, we do proof. Well, proof, let me sketch the proof later, but let me do example to show you this is powerful. This is really powerful, okay?
What's the intuition?
It's not so simple. There's no simple intuition, actually. I don't have, even now, I think I use it in my daily basis. I don't think the intuition. Okay, so it's come from that you have to work out this. There's no, per se, I don't know the intuition that, okay, how you come up with this very clever solution to this thing. But I can give you very simple argument, actually, why this is true. Yeah. Okay, since you asked, maybe I can do a short proof after, okay? But wait until I tell you short proof, and you tell me whether there's intuition or not. Okay. Right, let me erase this. And let me do one trivial example and one hard example. So, a free chiral, example number 1. A free chiral You know what's the R charge of a free chiral, right? But let's use a maximization to do the value, okay? Let the trial R charge of phi be R. So R of the fermion component is R minus 1. So 32 over 3 A trial is 3R minus 1 cube minus R minus 1. You agree? This is my trial function. Can you tell me where's the unique local maximum? So a trial has a unique local maximum at R equal to 2/3, which what you expect for a free chiral. So this means that it gives you the correct dimension. Delta equal to 1 for the free field. Okay? So this is a trivial example, of course. And now let's do the, okay. This example is a bit more complicated. Maybe I can postpone it to next time. Okay, since we have 10 minutes, let me sketch the proof then, okay? So this example is next example is one gauge group with 4 chiral, with 8 chiral. So we're gonna split it in some way, but this has a very nice feature. This example was really new actually, but okay, I don't think I can go through all the features, so let me do a short argument why this is true, why this. To give you argument for A maximization. Oh, did I erase? It's okay. So argument for A maximization. You observe that I hate the word proof usually. In physics, I mean, there's always a loophole. When you prove something, there's some caution. You have to be careful. So that's why I don't use the word proof on a blackboard. I don't like this word in physics, but people use it. So when people use it, I will follow the literature. But if I write it, I will say the argument for the A maximization. Even A maximization, there is something you have to be careful. Maximization. This I will warn you in the next lecture. So if you look at this A trial, you can compute derivative with respect to SI, okay, as follows. We have 9 trace trial square Fi. So you have to use this along with the RT equal to R0 plus sum I SI Fi. Okay? Use this along with this. You will get this. Okay? This is the first equation. You also have the second equation. If you compute the second derivative of A trial, you get 3 over 32 times 18 times trace of R trial Fi. Okay? Fi Fj. Okay. We want to show that when RT equal to R star, Okay? So you go to special point. So you flow to this special point, superconformal point. You have condition. Number 1, 9 of R star. We have nine of trace R star square Fi equal to trace Fi. This is the point number 1. So if we manage to show this, you agree that the first derivative is 0. So it's a maximum, local maximum or minimum. But we want to supplement this with another condition that trace R star Fi Fj is also less than 0. This is condition number 2. If you manage to show number 2, you plug it in, you see that this is negative, so it's a local maximum. Okay? So this is what we need to show. Again, showing this is highly non-trivial. You have to look at the various anomaly and use superconformal algebra. Superconformal algebra luckily has been worked out by people, which allows you to relate many things, notably by Osborne. This is, for example, in reference 39. This is, 98. Okay, this is also a complicated paper. I wouldn't say that it's highly non-trivial result. So basically, look at the first equation. We look at equation number 1. Okay, so equation number 1. It's related triangle anomaly. So these are the triangle anomaly, you agree? So let me write it like that. So on the left-hand side, you have R star, and then you put Fi on here. So you look at this anomaly, okay? So, and you remember that R star is in the same multiplet as energy momentum tensor. So compute trace of R star square Fi will be related by supersymmetry to the 3-point function T, Fi. This is by supersymmetry. Again, this is only a sketch of proof, so you have to look at detail later. Okay? Now, because you can replace the R current by energy momentum tensor. So this, computing this anomaly is amount to compute this 3-point function. Once you do that, this is proportional to the another anomaly, which is current of the Fi with the gravity square. This is highly non-trivial. Okay, this result is from Osborne. Okay. However, this is proportional. Well, this is a what? This is a triangle anomaly, right? This is a trace of the U1 Fi. Right? This is anomaly, what we call gravity Fi. Right? This is, you just compute the trace of U1 Fi. And then you see that this proportional to this is the equation number 1. How do you fix the coefficient? You fix it by looking at free chiral, because you already know the answer for free chiral. So you know that trace of R star square of Fi has to be proportional to trace of Fi. Okay? This is by this line of reasoning. And then you fix C using free chiral. Using a single free chiral. Okay, Recall that R of phi is 2/3, right? So this minus 1/3, and you plug it in, you can see that C is equal to 1/9. It's 9, yeah. So this is a sketch proof of the point number 1. Okay? So at this stage, I would say that this step, for example, is highly non-trivial to go from here to here. The intuition is that the T and the gravity, the curvature multiplet are living together. This is the intuition you should have, right? Because the T is related to Weil and Euler, the T mu mu. This is why you can replace this 3-point function with this gravity. But to do it properly, you have to use result of Osborn. Yeah. So now this part is related by Susi. This I show you, and this part is just anomaly, the triangle anomaly by definition. This you plug in trial. This is you plug in the fermion for 1, and then you can fix the C. Okay. Is this? So this is how to show number 1. Number 2 is a bit more complicated. So I don't think this is intuitive. Yeah. Then, yes. So the second one, again, let me sketch. So you can relate. So you see, the trick was, you look at this, you replace by TT. Can you guess the second? Instead of looking at that, here you look at TTF. RFF is TFF, right? Because R and T are in the same multiplet. So you look at another 3-point function. Now it's not TTF. You look at TFF, okay? So let me do the second one. I agree it's really sketchy, but this is the best I could do. I mean, without introducing the full-fledged conformal algebra in front of you, okay? But the rest, I invite you to read original paper anyway. But this is an idea.
You proved 1, now suppose that we proved 2. With that, we know that the derivative of a trial has a maximum.
Yeah.
But how do we prove that the U1 R star current is a subgroup of SU2/1?
Because
That's the thing that we want to prove, no, in the end.
No. Because if this is satisfied, you agree with me, right? So you said, but if this is maximized, then you determine this coefficient, the correct coefficient, which is turned out to be R star, because A has to be R star, right, at the superconformal point. I leave this as an unknown. I say that if it maximizes this, you determine the correct R star, because you use this into R, you plug this into here, right? You have a function of S, and you do these two processes, you go back to the original question of the R star, right? This you agree? Yeah. The original question has written in R star. The A without trial here has to be R star, and that determines the S at the value of R star. Okay?
Then how do we know that this R star is ABJ anomaly free?
R star is an.
How do you know that the R that they find from here is anomaly free?
Oh, I have to assume that it's there. If there is, this has to be satisfied. So you ask, repeat your question again.
I mean, how do I understand that this one I found that maximizes A?
Because if you agree that this linear combination has one variable to determine, right? One set of unknown, the SI. Yeah. So basically, once you plug in this into here, you have to manage to rewrite everything into terms of R star, right? Which S that gives you the A, which is equal to 3/32, 3 trace R star. You compare these two equations, right? The whole point is that you plug this in, you want to recover this equation. This equation has to be used at R star. And there is one value of S which maximizes this A trial that make you go back to this equation. That's the point. Okay?
But is it obvious that there's a unique maximum?
Yes, because of cubic.
Oh.
So let me try to, oh, I'm running out of time. So okay, so point number 2, let me go quickly and I'll finish in 3 minutes, okay? I'm happy to take questions during the break and I'm still here until also Friday after the discussion session, okay? So this is related to, by Susie again, to TFF. T of J, Fi, Fj, okay? And this you replace T with a gravitational as usual. Gravitation, JFI, JFI, Fj, okay? And this, you compute basically, this is basically Fi, Fi, right? So basically, yeah. So you compute this guy, JFI, Fj, okay? So if you look at this, let me put the J to be precise. Fj, okay? And if you look at this, this is proportional to some metric, 1 over x to the 4. Some of you already seen this thing in my note when I compute Wessel-Milano model. It has a 1 over 4, but this proportional constant has to be positive definite. This is the metric on the basic 2-point function. So this is Tij is a positive definite. Okay? And you use this positivity to argue this guy, okay? So basically, again, you look at this and you see that it has to be proportional to this guy. You fix coefficient using, again, the free chiral field. So once you do that using the free chiral field, to fix the coefficient of proportionality, you have trace of R star, Fi, Fj will be minus 1/3 tau Ij. But tau has to be positive definite. Minus 1/3 is negative, so this is negative definite. Okay? So since it's negative definite, you can show that this is less than 0. Okay? So this is the element of the proof of the A maximization. So, yeah. And now once you plug this maximized value, you get back to the original R star equation. Okay? And that tells you that this is the true value of A at the local maximum. Okay, so I think I will end my lecture here, and tomorrow we have 2 more hours. I hope to give you a bit more example, and yeah, there is something one has to be careful in using this maximization also. I will give you, I will discuss the subtlety later, but thank you very much.